Hi everybody. Today we're doing a pure maths paper from winter 15, paper 31 of A2, pure 3. So let's get started. Okay, so in an inequality question, the best and sort of most reliable way to solve these is to square both sides. So you know that once you've squared something, the inequality, the absolute value signs kind of don't matter because x squared is equal to minus x squared. So let's just square both sides. So we end up with 4x squared minus 20x plus 25 is greater than 9 times 4x squared plus 4x plus 1. And now you see the absolute value signs have disappeared because if we just square that and square that, it might as well be brackets, as long as there are real numbers inside, which we're always assuming unless we're told otherwise. And there'll usually only be one question on complex numbers in these kind of papers. So these are definitely real, and so we can do this. And we juggle things around and we end up with 4x squared plus 7x minus 2 is less than 0. So this thing is a parabola, right? If it was an equality, we would say that this is the equation that governs the roots of, i.e. the points where it crosses the x-axis. So it looks like a smiley face parabola. And so essentially what we're doing is we're saying we have this parabola. Oh my God, we have this parabola and we're looking for the points, the part of the parabola where it's below the x-axis, so where it's negative. So we know that that's going to be between the roots, right? It's going to be between the places where it crosses the x-axis. So we can actually factorize this and just extract the roots. So we get 4x minus 1, x plus 2, it's less than 0. So the parabola itself will have roots x is equal to 1 over 4 and x is equal to minus 2. So obviously the range of x for which this parabola will be less than 0 is between those 2 points. So x must be greater than minus 2 and less than a quarter. And that's all. That's it. So it's best to get it in a parabola, have a look at the parabola. That'll give you some physical intuition for what you're required to find, because these inequalities can be a bit confusing when they look like the original question. Okay, question 2. This is extremely straightforward. So u is equal to 3 to the x, and we just have to know that if you have say 3 to the x raised to a power a, by the rules of exponents, this is equal to 3 to the ax. So therefore, this equation can be written as u plus u squared is equal to u cubed. And we're asked to solve it. So we can put everything on one side and say u cubed minus u squared minus u is equal to 0. U squared minus u minus 1 is equal to 0. And we can immediately we can observe that u cannot be equal to 0 because 3 to the x cannot be equal to 0 for any x. There's no number x which you could raise 3 to and get 0. In fact, you couldn't get a negative number either. So you could make it really, really, really small, but you could never actually get 0 unless you raise it to minus infinity. But infinity is not a number. So we can just divide by u here because we know it's not 0. So we get this quadratic, and then we just we solve it using the formula, and we get a half plus or minus the square root of 5 over 2. And again, we've got to just look at this guy. They love doing this, where you know, and you substitute in and you get sort of solutions which seem to make sense. But if you go back to your original you realize that some of them are just impossible. So here again, 1/2 plus square root of 5 over 2 is fine, but 1/2 minus square root of 5 over 2 is less than 0, and so it cannot be the value for u. So we only take the positive root. And you will, that's what you get points for, is recognizing these two things about cannot be 0, cannot be negative. Oh, we're missing question 3 here. Okay, so, well, I might as well just, I'll just check if maybe it's gone onto a different slide. No, okay. Right, so question 3, I can look at it somewhere else, but it's about, we're given two equations, the tangent function and these two angles. So we're told that the tan of theta minus phi is equal to, and the tan of theta plus the tan of phi is equal to 1. And we're told to solve for theta and phi. So these are basically simultaneous equations, but for this one, you might want to use one of the trigonometric identities. So we know that this is equal to the tan of theta minus the tan of phi all over 1 plus tan theta tan phi, which is equal to 3. And then we can replace tan phi by 1 minus tan theta, right? So we have tan theta minus 1 minus tan theta all over 1 plus tan theta times 1 minus tan theta. And you will find that this gives, once you've sort of rearranged it, you get 2 tan theta minus 1 is equal to 3 plus 3 tan squared theta minus 3 tan theta. Blah, blah, blah. It's a quadratic. You know how to solve it. You solve it to get tan theta, and then you use this equation again to get tan of phi. And that's all there is to question 3, which, sorry about that. Technical difficulties. That slide must have fallen off. But that's question 3. Okay, question 4. So we're asked to localize where alpha is. Any of these kind of things usually involves guessing a bit. We're told that it's real and there's one root. So we're just going to try integers. So I'm going to start with a positive integer. I'm going to try x is equal to, this is question I. X is equal to 1. Well, then I get 1 minus 6, which is equal to minus 6. Well, that's obviously not 0, so it doesn't quite satisfy it. So instead I try x is equal to 2, and I get that the function is equal to minus 2. Now this is better. That means I'm moving in the right direction. So I don't need to try negative numbers or 0 or anything. Obviously, 0 wouldn't help either. So this is good for me. Like, I know that I must be moving in the right direction. But let's try x is equal to 3 as well. And I get that this is equal to 12. So that's too far. I'm looking for 0, and I go from minus 2 to 12. So it must be in the real root, must be somewhere there. So alpha must be greater than 2 and less than 3. Now, in the second question, they've given us an iterative formula. So these are the formulas where you start with a guess, and then you calculate this number, where you plug the guess into xn, and then you calculate xn plus 1, and then you take that number and plug it back into xn, blah, 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 and you keep going until the number that you keep coming out with changes less and less with each iteration. And the number of decimal point precision that you need is the number of decimal points which haven't changed in a couple of iterations. So what does it mean for a formula to converge to somewhere? Well, if it converges, then xn plus 1 is equal to xn. So each time you do the formula, you get the same number over and over again. It converges to that value. So we're going to say that if it converges, then we're just going to say xn plus 1 is equal to xn. Six over x. You get x cubed minus x squared minus 6 is equal to 0. So that's the same formula as before, and that's enough to show that it converges to alpha. So alpha is a root, therefore an iterative formula will converge. Therefore these things will be satisfied, and if they are, then you get the original formula, which makes sense, right? Okay, so now they're just asking us to plug everything in, and I think you can do that. That's just really, really boring number crunching. Try, I mean, we see that 2 is probably closer to what alpha is, because we get minus 2 here as we get plus 12 there, and we're looking for 0. So try 2 first in xn, plug, plug, plug. Give each iteration to 5 decimal places, so you know the whole thing is laid out. And then when you find a couple of iterations where the first three decimal places have not changed, then you know that you're close enough. Okay, question 5. So we've got that y is equal to e to the minus 2x tan x. Now this is just product rule. Dy dx equals, so I'm going to differentiate the exponential first. So that's minus 2 e to the minus 2x times tan x plus second term e to the minus 2x, don't touch it, tan x differentiated is sec squared x. And I'm just going to gather this in so it looks a little neater. E to the minus 2x minus 2 tan x. And then for sec squared x, I substitute 1 minus 1 plus tan squared x. And then I notice that this is going to be of the form, x squared minus 2x plus 1. Well, I know that that can just be written as 1 minus x all squared. So this is 1 minus tan x all squared, and we're done. That's all that is required. Knowing what sec squared is, knowing how to differentiate these two things. The derivatives are in the formula booklet, don't worry. And knowing how to rearrange it in this form, and that you can make that into a square. So the second part is to explain why the gradient of the curve is never negative. So that's why they made you put it into this form. So your argument would run something like e to the minus 2x is greater than 0 for all x. And that's true. You can never raise this to anything which makes it less equal to 0 or less. You can never raise anything to a power which makes it equal to 0 or less, as we've seen many times before. And anything squared is greater than or equal to 0 always, if it's real. So let's just actually, in all these cases, I don't know why it keeps doing that when I rub stuff out, but we'll deal. Why? But why? I swear. Isn't that interesting? Anyway, I'll just write that again. So for all x in the real numbers, just to be clear, of course, we're always dealing with real numbers in these questions unless they tell us otherwise, but still. So e to the minus 2x is always greater than 0, and 1 minus tan of x squared. So, I mean, I put x just to mean anything, but maybe I should put, let's make it more general. e to the a, and see, yeah, it goes away in the end. Really odd. So a squared and e to the a always have these qualities for all real a. So therefore, obviously, this thing has to be greater than 0. This thing has to be greater or equal to 0. So dy dx, the smallest it can be is 0. Cannot be negative, and that's the argument. So now they're asking us to find the point where the gradient is least. So obviously, this is going to be the point where it's equal to 0. And we've seen that e to the minus 2x can't equal 0, so this thing must equal to 0. And this is solved by x is equal to pi over 4. So that'll give tan of x is equal to 1, which gives this whole thing equal to 0. Okay, question 6. So this is another one of those factorisy ones that we've seen before. So what does it mean for something to be a factor? It means that this bracket, this x is equal to minus 1 is a root. So if this is a factor, it means that if I divide this whole business by that, then I will get no remainder. If I divide it by that, which is not a root, I will get remainder 1. So this is pretty straightforward to do. We're going to say, let's call this is called p to p of x. So we know that p of minus 1 is equal to 0 because it's a root, it's a factor. So if we evaluate it, we get minus 8 plus a minus b minus 1 is equal to 0. So we have our first equation, a minus b is equal to 9. That's number 1. And we know that p of minus 1/2, that's if x is equal to minus 1/2, we will get a remainder 1. And this is minus 1 plus a over 4 minus b over 2 minus 1 is equal to 1. And that's our second equation. We get that a minus 2b is equal to 12. So if we solve our simultaneous equations by going 1 minus 2 to get rid of the a's, we get that b is equal to minus 3 and a is equal to 6. And that's all there is to it. 3 lines for 5 marks. I think you probably. The second one is actually more annoying because you have to do one of these factorization divisor things. So now our equation reads 8x cubed plus 6x squared minus 3x minus 1 is equal to 0. So we know that if we divide this by x plus 1, we should get we'll get no remainder, and we can work out the other roots. So let's divide this by x plus 1, and I do this by going 8 as I have before, 8x squared. So I sort of separate out one of the x's from here, and I force it, and I actually set it to x plus 1, and then I mop up the extra stuff that comes out. So 8x squared times x plus 1. Now this will give me 8x cubed, but it will also give me an extra 8x squared. So I have to subtract 8x squared plus 6x squared minus 3x minus 1 all over x plus 1. So this will give me 8x squared, because that cancels with that for the first term. And I've got minus 8 plus 6, that's minus 2. And I extract one of the x's out, and I force it to be x plus 1. But this will give me an extra factor of minus 2x, so I have to go plus 2x. And then the remainder, minus 3x minus 1. And this is all over x plus 1. Then I get, so that gives me 8x squared, and then minus 2x for the second term. Then I've got plus 2x minus 3x, which is minus x. So I get minus, and then I force that x to be x plus 1 minus 1 over x plus 1. Well, that guy is just cancels. Right, sorry, that guy cancels with that, but I had to actually add a mopping up term. So this gave me an extra factor of minus 1, so I have to go plus 1. And then there's the minus 1 that's already there, so those guys cancel. This guy just becomes 1, so we have that 8x squared minus 2x minus 1 is equal to 0. And so we can solve for the other two values of x, and happily it's very factorizable for x plus 1 and 2x minus 1. And those are our solutions. So we've managed to find the other two factors and factorize it completely. So if you want to, just in case they're a bit mean, but you can write that p of x is equal to x plus 1, 4x plus 1, 2x minus 1. And that's completely factorized. Okay, vectors again. So we have one of these situations where we have a line and a plane, and we're asked to ascertain how they interact with each other. So let's draw redrawing. This is not going to be like accurate to actually where the points are. I'm just doing this for illustrative purposes. And then we have A over here, maybe. That's the origin, by the way. Maybe B over here. And then I'm saying there is a plane. Like so. And they're telling us that there is a line going from A to B, and that's at right angles to the plane, and that there's another point C somewhere on the plane. So this is our situation. This point here we'll later see as n. So we want a vector equation for the line passing through A and B, first of all. Well, a general line, so say line L, will have the equation which is equal to some point on the line plus a parameter, call it lambda, times the vector along the line. And as I've said before, the logic of this is that if I want to get the origin to some random point on the line, I need first a vector which will take me to the line, and then one which will move me up and down it however much I need, up or down, or negative values of lambda. So here I have a point on the line, let's say A. And then I want a vector along the line. Well, the vector from A to B is that. And the vector AB is given by B minus A. And you remember that if I want to get from A to B, it's the same thing as going backwards from A to the origin. So that's minus A plus B. So that's equivalent to going just zipping straight across there. It's completely the same vector if you go there and there, or just go straight across. So it's minus A plus B, or B minus A, whatever. So that will give us 1, 2, 0 plus lambda 2 minus 2, 1. That's all there is for that question. Now, sub-question 2. You want the equation of the plane M, and planes are usually given, instead of this kind of vector equation, they're usually given as one of these, that any point which is on the plane has to obey. Any point x, y, z has to obey this equation. So the quickest way to do these is to recognize that this A, B, and C define a normal to the plane. So if I have a vector A, B, C, that is going to be sticking out of the plane at a right angle. Well, I already have a vector that's sticking out of the plane at a right angle. I have B minus A, or AB. So I'm going to say that that's this one here. That is AB. And that is normal to the plane. I know it doesn't quite look like it on my diagram, but it is. There's a right angle, so you can see it. So I know that my plane equation is going to look something like 2x minus 2y plus z is equal to d. I just need to find out what d is. Well, if this equation is obeyed by every single point on the plane, then any point on the plane, if I plugged it in, should give me the correct value of d. So I have the point C. So I plug in the point C, and I get that. So you will get 2 minus 2 plus 4 is equal to d, or d is equal to 4. So that's all we need. We have our equation 2x minus 2y plus z is equal to 4, and that's the equation of the plane. So this is the best method. If at all possible, use something that you know is the normal. They usually will give you one, and then plug in a point. So for the last question, they're asking us to find the coordinates of n, and then show that the distance between n and c is square root of 13. So what is n? It's the intersection of a line and a plane. What does that mean? Well, it means that the coordinates of the point will obey the equation of the plane and will obey this vector equation of the line. So some point n is going to be on the line, so it's going to be equal to 1, 2, 0 plus some lambda n, some number, times 2 minus 2, 1. And I will just express that as 1 plus 2 lambda. I'm just going to write who's got the time. 2 minus 2 lambda and lambda. And now this obeys the plane equation. So let me plug that into the plane equation. 2 times 1 plus 2 lambda, that is a 2. Minus 2 times 2 minus 2 lambda, plus lambda is equal to 4. And this will give you lambda is equal to 2/3. Well, great, we're almost done. So we know n, we know c. So we can find out Cn, and that's just going to be equal to n minus c. Because remember, to get from n to c, you go backwards along n and then up to c. And this is going to be equal to 1/3 4 minus 1 minus 10. And then you just take the magnitude, Cn. And it's going to be 1/3 square root, and it's Pythagoras 4 squared plus 1 plus 100, blah, 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 square root of 13. And you're done. Okay. So question 8, this is a full 9-mark question. But once you've got the trick of it, it really won't take you that long. You can do it in just a few lines. So like most of these differential equation questions, it first requires you to separate variables. And this one requires you just to be a little bit clever with trigonometric functions. So we separate variables first. So we get dx over x plus 2 is equal to sine squared of 2 theta d theta. Now this guy looks fine. We'll get a natural log function, but this guy, bit tricky. We don't mind if there's stuff inside we don't mind the 2 theta. The 2 theta is fine. We know how to do that. It's the squared which is bothering us. And the trick here is to recognize that the cosine of 2 theta is equal to 1 minus the sine squared of theta. So if sine squared of theta is now sine squared 2 theta, that means that cosine of 4 theta is 1 minus sine squared 2 theta. And now we can plug in for sine squared theta. So we now have 1 minus 2. 2 sine squared 2 theta. So we have 1/2 1 minus the cosine of 4 theta d theta. And now we just need to integrate. Probably prettier than that. Integrate. And we will get that the natural log of x plus 2 is equal to 1/2 times theta minus 1/4 sine of 4 theta plus c. So we need the c, so we apply our boundary condition that x is equal to 0 when theta is equal to 0. So we get the natural log of 2 is equal to c, and we just put that in there. So that's our equation, no problem. And then we're asked to calculate the value of x when theta is equal to pi over 4. So all we need to do is raise everything here to raise e. Well, we take the log of both sides, so we get that x plus 2 is equal to e to the 1/2 theta plus, minus 1/4 sine of 4 theta, and there was the sort of e to the natural log of 2, so that just becomes 2, and then so x is equal to 2 times all that business minus 2, and then you just plug in pi over 4, and you'll get your answer. It wasn't so hard, was it? Like 9 marks in the bag for that. It's just this little trick with the trigonometric identities. It is given in your formula booklet, but seeing the 2 theta and to trying to get into terms of theta, but rather in trying to get rid of the squared, like do everything you can to get rid of the squared, because that's not easy to integrate with trigonometric functions. You don't care if it's 4 theta inside there, you just want to get rid of the square. Okay, so now we have a complex number question, and it starts off by talking about the Argand plane. So we will draw that. So this is plotting the imaginary part of u, and this is this is the real part of u. So u is 3 minus I. So the real part is a 3, and the imaginary part is a minus 1. So u sits there. Now u star, this is the complex conjugate of u, means that you just switch the signs of all the i's, so you get 3 plus I. Well, that's just going to be over here, u star. What about u star minus u? Well, u star minus u is equal to 3 plus I minus 3 minus I, which is equal to 2i. So you see, it's just kind of, it's got rid of the, so it's equal to twice the imaginary part of u. If you add, just a side note, if you go u star plus u, then the imaginary part, the real parts will double up, because the real parts don't change sign under conjugation. And the imaginary parts will cancel out because they're both of opposite sign. So we've just got u star minus u is 2i, so it's just double the imaginary part, and it's on the axis there. So that's u star minus u. And they're saying what shape is this? And I think it's perfectly fine to say that that is a parallelogram. I don't know why that's important, but there you go. So in the next question, they're asking us to express u star over u in the sort of Cartesian form, x plus iy. So what is u star over u? Well, it's 3 plus I over 3 minus I. Now this is not immediately separable into x plus iy because you've got imaginary stuff in the denominator. Always get rid of all the imaginary stuff. And how do we do this? Well, it's this old technique. We know that for that u star, so if you take a complex number and multiply it by its complex conjugate, this will be a real number. And we only want real numbers in the denominator. So let's multiply this by the complex conjugate of u. But then we can't just multiply it. We have to make sure that everything is consistent. So we just do that, because of course this whole thing is just equal to 1. It's something divided by itself. So timesing something by 1 doesn't change it, so this is allowed. So on the bottom, in fact, if some number w is equal to x plus iy, then w star is equal to x, w star times w star times w, this thing we're just working out, is equal to x squared plus y squared, because we're multiplying it with, by x minus iy. The middle terms cancel out and the opposite terms square, and the I squared is -1, and there's already a minus there, so it becomes plus, so on. So we know that instantly this thing at the bottom is 9 plus 1. And on the top, we've got 9 plus 6i minus 1. So this whole thing is 8 plus 6i over 10. But they want it in the sort of separated form of x plus iy. So I'm going to instead say that that's 4/5. Whoops. 4/5 plus 3/5 I. And that's our x and y. Now, question 3. So they're talking about the argument here of this complex number, because a complex number divided by another complex number is still a complex number. So they're asking for the argument of that. Now, the argument is the theta part of the polar expression of a number. So if z is equal to x plus iy, it's also equal to r e to the I theta, where r is equal to the square root of x squared plus y squared, and theta is equal to the inverse tangent of y over x. Now, if you haven't seen this before, if you have seen it before, just ignore the next minute, but on the Argand plane, if I have some number there, this is the x coordinate, and this height is the y, so this forms like a right-angled triangle, right? The hypotenuse is the r, the radius, and this angle is the theta. So if I want to get to a certain point, I can either go east x miles and north y miles, or I can just rotate by theta and head out for r miles. So in order to get r, it's the hypotenuse of that triangle. So that's Pythagoras, very familiar. And the same thinking goes behind the inverse tangent. The tangent of theta is y over x, so just take the inverse. This is the argument of z. So what is the argument of u star over u? Well, it's going to be the argument of 4 over 5 plus 3 over 5i. Well, this is the y. So that's equal tangent for what's going on with this other side. The fact that if you multiply, or say divide, two numbers together that are in the form of exponentials, you add or subtract their exponents. So e to the a divided by e to the b is e to the a minus b, right? So if we're saying that u is equal to some radius r, don't care what it is, e to the I theta, then u star is equal to r e to the minus I theta. Because remember, when you star something, all you do is switch the signs of the i's. Like, that's straightforward. It doesn't get weird just because you're doing exponents. You just switch the signs of the i's. So u star divided by u is the r's cancel, and you get e to the minus I theta minus I theta, which is e to the minus I2 theta. So what's the argument of this? Well, the argument is just it's minus 2 theta, where theta is whatever the argument was of the original one, of u. So argument of u is the inverse tan of the original u y value, which was -1, divided by the original ux value, which was 3. So we're saying that the argument of u star over u, so a new expression for it, we already worked out one way of expressing it. This is another way. Argument of u star over u is -2 times the argument of u and this is almost good enough. And we realize that the tangent function is sort of anti-symmetric around the origin. So it's like the sine function. The tan of -x is minus the tan of x for these for values between minus pi over 2 and pi over 2. So in this little range, it's kind of reflected around the x-axis. So the minus sign comes outside, and that becomes 2 inverse tan of a third. And that's how we show that those two things are equal. Okay, we're making good time. Question 10. So we're looking at a curve and we're finding a maximum point. So the first instinct is always, of course, differentiate. So let's differentiate this, this curve, dy dx. We're using the product rule, so that's 2x, or let's use the quotient rule. So 2x, 1 plus x cubed minus 3x squared times x squared all over 1 plus x cubed all squared. And then we can do a little bit of cancellation, and this gives us 2x minus x to the fourth over 1 plus x cubed all squared. So we know that, actually, I'm actually going to take an extract an x out here, so it becomes 2 minus x cubed. And the same thing's good. So we know that at critical points, dy dx is equal to 0. So these could be maxima, minima, saddle points, inflection points. So it could be any of these. And if we set this equal to 0, so we will get either x is equal to 0 or x is equal to the cube root of 2. And we can see by inspection which one it is. Like x is equal to 0 is obviously where this function is having a minimum, and m is where it's having a maximum, and it's not at 0, so it's going to be the x is equal to cube root of 2. Some integration. You got to remember that the key fact is just that the area under curve is the integral of that curve. It's another conception of the integral. So we want to integrate this curve between p and 1. So we have the area integral of later on, it's useful just to put the dx on the left-hand side, so dx, because then you might have something really, really long and you don't want to forget dx. And maybe sometimes you want to make it clear that you're going, you know, dx, dy, dz, d theta, maybe you're integrating loads of things at once. So it's best to just stick them all in the same place at the beginning, you know, just for bookkeeping. It means the same thing. So r is the integral dx of y of x between 1 and p, and we're requiring it to be equal to 1. So we are integrating between 1 and p x squared over 1 plus x cubed dx. Now, if this looks, insane to you, just realize they're not going to give you something that requires you to look it up in an integration table or, go through some heavily long derivation. Usually, in fact, most of the time, these are situations where you've got the integral of f prime of x over f of x dx. And this is always equal to the natural log of f of x. And that's all they ask you to recognize. And you should remember that this one, as I mentioned before, is just a special case of that one, where f of x is equal to x, and therefore f prime of x is equal to 1. So here we notice that I can write this as 1 over 3 times the integral from 1 to p of 3x squared over 1 plus x cubed. So I've sort of introduced and taken away 3 at the same time. And this thing is obviously the derivative of this. So this is all equal to 1/3 natural log of 1 plus x cubed. And we're told that's equal to 1. So therefore, the natural log of 1 plus x cubed is equal to 3. And now we just take the natural log of both sides. We go 1 plus x cubed is equal to e to the 3. Therefore, x is equal to the cube root of e to the 3 minus 1. And that gets you the correct answer. That is the x that is required. Sorry, I don't know why I left it x. Oops. That's very, very silly of me. And that would have been very much a mistake they're looking out for in the exams. So here, I'm just going to be super careful. Actually, it won't make a technical difference, but I should do that. 1 to p. So that's 1/3 natural log of 1 plus p minus natural log of 1 plus 1. Is equal to 1. And this I can always refer to as the natural log of 1 plus p over 2, just drawing the logs together, is equal to 3. And there's a million ways to do this, but you end up with p is equal to the cube root, so p rather than x, 2 e cubed minus 1. So it's a factor of 2 that I didn't get last time because I forgot to take the lower limit as well. And there, that'll give you the correct answer. Please let me know if there are any questions you have about any of these things, and I will see you next time.